This is the Singapore Math Live Solutions recording for Primary 5. This is the second week challenging word problems, page 8 through 11, and we are still in whole numbers, but these are the challenging problems. Now when Singapore Math says that they are challenging problems, what they mean by that is they are challenging problems. And so as we tackle them, keep in mind that they are not simple, but they are well worth the time and investment in watching them. I personally told my own children when they went through these, sometimes it was enough for me if they just saw me work them and really understood how I got through them logically. If your child cannot do every one of these problems all by themselves, they can still be an excellent mathematician by the end of the Singapore Math curriculum. However, I strongly urge you to ask your child to sit down and just logically think through each of them. They could do it by watching this recording at this age, or you can do it, learn it, see what I'm doing, and follow the same logic and demonstrate it for them. I would love to think that all of your kids would see all of these solutions, even if they can't work them themselves. Now, I've just scared everybody, and I didn't intend to do that, and yet, as I said before, the this whole numbers portion is hard, partially because we're not doing math, we're thinking math. That's good for us. Feels like work, it is work, but it's good for us. First problem, I already started out by drawing some of this down for us so that we would have it in front of us instead of me drawing it as I was talking. It tells us that there's a number x that's divided by the number y, and the quotient, the answer to the division problem, is 16 with a remainder of 3. Now we don't often think about math this way, but I drew a picture so you can see exactly what we mean by this problem. The number x is represented next to the word x right here. This is the value of x right here. And what they told us is that x can be represented by 16 y's and 3 left over. Here it is in words. X is divided into groups of y. There are 16 groups of y and 3 left over. That's what we mean when we say x divided by y is 16, remainder 3. One of the things I love about Singapore Math is it helps us to understand what it is we're doing when we do the math. And that's what it means. And then, of course, the number y is represented by y. That's all it is. So then look at the next sentence. The sum of the two numbers and the quotient and the remainder is 345. The sum of the two numbers and the quotient, that's 16, and the remainder, that's 3, is 345. And we're trying to solve for x. Now, this looks like an algebra problem to you and me. And if I have students listening in, just know eventually you'll get some problems that look like that, and there'll be an algebra problem. For right now, we're not making it an algebra problem. We're making it a logic problem. If x and y need 19, let's just make that 19, to be 345, then what we know is x plus y by itself without that 19 must be 19 less than that. Now remember in Singapore Math, when we talk about math, mental math, to do 345 minus 19, think about taking 20 away and giving 1 back. So if I took 20 away, I'd be down to 325, but I don't want to quite take 20 away. I want to give 1 back, so I have 326. Mental math skill, always good to keep those in mind. So I get down to the fact that x and y equal 326. Well, what do I know about x? I know that x is 16 groups of y. So 16 groups of y plus 3, by the way, plus another group of y, need a y in there, 16 groups of y plus 3, that's what x is, right? If I say x is 16 groups of y plus 3, I wrote it out in words here because I didn't really want to draw that picture again. Okay, so 16 groups of y plus 3, can't forget the 3, plus 1 group of y, and that's equal to, I ran out of space, so I'm going to put it on this side, 326. Okay, so then taking advantage of technology. I felt like that was too messy, so I erased it and rewrote it, paused the recording, and now we're back. 16 groups of y plus 3 is what we're calling x. Plus y is 326. Well, now I could say I have 17 groups of y, and 3 more than that is 326. Again, same logic. If I have to add 3 to get 326, then it must be true that 17 of these y's that I have is equal to 323. Well, if I take that 323, and I know that's 17 equal groups, if I divide 373 by 17, I found out that each group of y must be equal to 19. Now, I didn't show that math. That is 323 divided by 7, and that would give us a value of 19. So I know that each of my groups of y is 19. Now the question is, am I finished yet? And of course the answer is not quite. I have to finish a problem because the question asks me what is the number x. And the number x is 16 y's, and y, remember, we just found to be 19, plus 3 more. Now again, some math involved there, but the answer to that is 307, and that is the value of x. Now you see why Singapore Math is a lovely preparation for algebra, because we are doing logically what could be written as an algebra problem, and many times students get confused by algebra problems, but if we train our kids to see this and understand this, then what logic that algebra presents will be very obvious to them, and they will not struggle with it because they truly understand, like I don't think other curriculum helps students understand what we mean when we say x divided by y is 16 remainder 3. That's a wonderful thing to clearly understand what we're talking about. Problem number 2. We have an odometer. The odometer at the beginning of the trip is 12,321, and they introduce the word palindromic number. A palindromic number is a number that reads the same backwards and forwards, just like a palindrome is a word that is spelled the same backwards and forwards. And so the parameters of our problem, it's just a logic problem really, we're going to drive for 2 hours and it's going to show another palindromic number. And so the question is, what is his speed? So if we have, if we're going to drive for a couple of hours, and it says we're going at speed less than 100 kilometers an hour, if you're going at 100 kilometers an hour for 2 hours, then you go 200 kilometers. That's logic. And so I can't go any more than 200. Matter of fact, I can't even go 200 because it says he's driving at a speed, or driving at a speed below 100. So my distance is going to be smaller than 200. And I say that only to say this. 12,000 is a pretty big number. I'm not going to change these first 2 digits. And if those first 2 digits don't change, then the last 2 digits are going to stay the same as well. Because after all, it's a palindromic number. It has to start with 1, 2, which means it ends with 1, 2. So there's really not a lot of choice. I must have a 4 in the middle. Now, if you want to stop and think, now could I have a 5 in the middle? Well, the only problem with that is that gives you a distance of 200 kilometers. And we said over here, can't have that because we're going for less than 100 kilometers an hour for 2 hours, so I have to go less than 200 kilometers. So if your student thinks ahead and thinks, well, do I know for sure that this is the answer, 4 is the right number there? Yeah, we do, because the parameters in the problem made a 5 in this spot, 12,521 miles or kilometers. It made that an incorrect solution because of all of this information. So if my answer is 12,421, look at the question, what was his speed? Well, at this speed, he went 100 kilometers in 2 hours, and so that is a speed of 50 kilometers per hour. And so the answer, of course, is 50 kilometers an hour. problem number 3 I also got started just so you save us the time of looking at it and drawing it out online. We have 8 adults here. The question is, the product of the ages of 2 adults is 770, and we want to know the sum of their ages. So here's what we have to realize. I want to know all of the numbers. I want to find all the numbers whose products are 770. Well, you say, you could have 1 times 770, or you could have 2 times 385. That's true, you could. But keep in mind the other part of the question. These numbers are going to be the ages of adults. Clearly, 770 doesn't work, 385 doesn't work, even 1 and 2 don't work because those are not ages of adults. So I'm going to start by breaking it down to prime factors. 770 is 77 times 10, which is 7 times 11 and 2 times 5, and each of these are prime numbers. Now, what that gives me, and this is something, again, about number theory that you may or may not have completely realized yourself, but all the products that add up or that multiply to be 770 are made up of those 4 factors. And so I picked some that are going to be adult ages. Clearly 7 by itself, or 11, or 2, or 5 by themselves are not adult ages. I'm going to have to pair them up. So I could pair up 7 and 11 and 2 and 5. I could pair the 7 with the 2 and the 11 with the 5, or I could pair the 7 and the 5 and the 11 and the 2. Now if you stop and think about it, those are the only ways that I can pair up these numbers in pairs. This would mean that an adult is 77 and the other adult is 10. But you know, that doesn't make any sense because 10 is not a good age for an adult. So we're going to say that that answer is not an option. This one gives me 14 for an adult and 55 for an adult. By the same logic, I don't consider a 14-year-old an adult, so I'm going to say that that's not going to be my solution. But this pairing gives me the number 35 and the number 22. Now those certainly qualify as young adults, but those 2 ages would represent adults. And so, again, go back to the question. The sum of their ages, 35 and 22, sum of course means you're going to add, the sum of their ages is 57. Now, if you wanted to check it, it would certainly be fine to go back over and say, well, 35 times 22, and find that sure enough, the product of 35 and 22 does give you 770, and those are 2 ages for adults. And so that is the way we solve that one. Remember that the prime factorization gives us all of the options that we have. I don't have to stop and figure them all out. I can find the prime factors and then put them in different pairings. Number 4, yet another one where I had to have a big group of information, so I wrote it out before we started. Start on the right side of the page with me. Number 4 talks about this. We're talking about a 3-digit number that has a remainder of 7 when I divide it by 9 and a remainder of 2 when I divide it by 5. All right, start on the right side of the page. A remainder of 7 when divided by 9 means that I'm going to add 7 to multiples of 9. Right? Multiples of 9 give a remainder of 0. So by adding 7, I get a remainder of 7. Again, this is remainder theory, and at the very least, I want you to be very comfortable with remainder theory. The second part of the problem, a remainder of 2 when divided by 5, means that you add 2 to multiples of 5. Now, I realize the problem is talking about 3-digit numbers. I want to start as simple as I can because I got to figure this out, and I'm assuming we're going to make a big guess that one thing I want to do is to find a pattern. And it's always easy to find a pattern. It's easier to find a pattern when you have numbers you can wrap your head around a little bit. So I'm just going to start. And I wrote the numbers I didn't worry about the fact that they're not three-digit numbers yet. I wrote the factors of 9 and I added 7 to them. So each time, if you follow straight across, the number on the right is a multiple of 9 plus 7. Okay. I don't know that I've learned a whole lot by having this, and actually I'm seeing I wrote that down wrong. Let me correct this one. All right, one thing that's always very careful is to make sure you don't write the numbers down incorrectly. So I had some errors in my number list when I wrote it down the first time, and I've corrected those. So this will work a lot better because we have the right numbers. Okay, so again, on the first part, on the left side of the left page, I've done the 9s. I have the multiples of 9, and I added 7 to them. And again, my goal here is to find a pattern. On the right side here, I have the 5s, and I'm adding 2 to the multiples of 5. Well, now the pattern on the 5s really jumps out at us pretty quick, right? Every one of these either ends in a 7 or a 2. All right, always helps to write things down correctly. There we go. Now I've got all my numbers correct. So the 5s have an obvious pattern. Every time that this second condition is met, a remainder of 2 when divided by 5, that always has a last digit, a digit in the ones place of a 2 or a 7. And when we think about it, that makes sense. But then look back at my 9s. That pattern's not quite as obvious, but there is in fact a pattern. I start at 6, and then 5, 4, 3, 2, 1, 0, and then I'm back to 9, 8, 7, 6, 5, and we can presume from that that I'm going to have a pattern of decreasing numbers. Now, for both of these conditions to be met, very simply, I have to have a last digit of a 2 or a last digit of a 7. Now remember, I'm looking for a pattern. When I'm looking for a pattern, I notice these two numbers are 9 times 5 and 9 times 10. And when I use those numbers and I add 7 to it, I come up with a number, 52 or 97, that is going to meet both of my criteria. Remember, my criteria is that I need a remainder of 7 when divided by 9 and a remainder of 2 when divided by 5. So remember, I started with I started with simple ones, with 2-digit numbers. I'm trying to figure out what's going to happen and how I'm going to get the answer in the 3-digit numbers. So I found my pattern, I checked my thing, and it's working out. And so the next thing I'm going to do, hold on to all of those thoughts, I'm going to check my pattern and say, well, I knew that it worked at 9 times 5, that was 45, and if I add 7, I got 52, and that worked. 9 times 10 was 90. I add 7 and I get 97. Now remember, as long as it ends in a 2 or a 7, I'm good to go for 5 as well. But both of these numbers are 2-digit numbers. But of course the next time, my best guess is that 9 times 15 might work. So I have 135, add 7 to get 142. That's going to meet both of my criteria, and I found a 3-digit number. 9 times 20 is 180. Add 7 to get 187, and again, I have a good answer. Now, do I really have to write this out all the way down to the end? Hopefully not, right? We'd like to think there's a shortcut. Think with me a second. 9 times 111 gives me 999, and that's the end of the 3-digit numbers. So the last one that I could use before that was 9 times 110. That would give me 990. If I add 7, I'm going to have 997, and that will be, pardon the square there, but 997 will be the last number that works. So I know that if I do 9 times 15, or 9 times 20, or 25, or 30, all the way up to 9 times 110, those are all the options that I have. And you can count those up in one of many different ways and find that there are 20 numbers that fit the category. There are 20 three-digit numbers that have a remainder of 7 when divided by 9 and a remainder of 2 when divided by 5. That is certainly, absolutely a problem that is full of discovery and requires, I like to say, a good soak. You just have to be willing to soak in the numbers, soak in the math, and soak in the logic for a while. It's not going to be obvious, it's not going to be easy, but it's good for them. I hope that your child is willing, and I hope you're willing to take the time to walk through that and just kind of soak in the math for a while and see it. I always told my children when we did Singapore math books, just because one problem felt hard, don't assume the next one's hard. It's not necessarily true. So that's good. Number 5 is a much more down-to-earth, normal kind of problem. And so let's look at that. We have an election, and there's 240 votes cast for 4 candidates. So I'm just going to call my candidates A, B, C, and D, and I have four votes, and so I know somebody won. I'm just going to let A be my winner. And it tells me that the winner won by a margin of 8, 13, and 15 votes. So maybe B was the second place person, and he got 8 fewer votes than candidate A. In C, that was my third place winner, and the third place winner had even fewer votes. They had 13 less than person A. And finally, person D did their best, didn't make a good showing. They had 15 votes left than person A. And altogether, I know that there were 240 votes cast. Now, I drew it this way because I want to make the point. In order to figure out how many votes were received, and this wants to know the lowest number of votes received by a candidate, there's a couple of ways to do it. I think the easiest way to do it is to make all of these numbers and get basically up to this far and get 4 equal blocks. So for example, what I have there is 240 block votes in the green. But if I were to add 8, then that would cover this one all the way out to there. And if I added 13 more votes, it would be like I'm covering this one all the way out. And if I add 15 votes, then I have all of these filled in. And all of a sudden, I have enough votes for 4 equal groups. When I add those together, I get 276. Now again, I don't really have these votes. Matter of fact, those votes are definitely missing from candidates B, C, and D. But if I put those votes back in, I'd have 276, and I would have 4 equal blocks. So if I divide it by 4, I find out that there were 69 votes for candidate A. Now we always have to go back to the question. It asks us what is the lowest number of votes received by a candidate. Poor candidate D, he had what A had, which is 69, but 15 fewer votes than that gave him a total of 54 votes for the lowest candidate. Now you can certainly check this. There's a little bit of math involved in checking it. If this is 69, then I know that this vote is 61. I'm just subtracting. This person must have had 56 votes, and this person we already said had 54 votes. And if we add 69, 61, 56, and 54, we're going to come up with 240 votes, which is going to tell us that, yep, we got all of it right, and we finished the problem correctly. Problem number 6. If this was an Algebra 2 textbook, we would set up 2 simultaneous equations and solve 2 equations, 2 unknown, and we'd make a real math problem out of it. Singapore math teaches us how to think about these kind of word problems without making an algebra equation out of it. In order to do that, they have to give us nice problems. Now, when your student learns Algebra 2, we will work with problems that are not so nice, and that'll be fine by then. They're ready for it. Right now, we're going to learn the concept with nice problems that make us happy and don't make us go crazy. Later on, we'll save the abstract for Algebra 2. But know right here, if you read this and you think, boy, this is too confusing, we can't do this, it's because you're trying to make it an algebra problem, and you're trying to make it way too hard. We have nice problems. They're really easy. Watch what happens. I have 2 watches and a calculator. This is a watch and another watch. And here's my calculator. And I know that that costs $49. By the way, are you surprised that I'm going to draw a picture? We always draw a picture, right? And then I have 3 watches and 3 calculators that costs $99. And the question they want to know is, how much is a watch? Okay, so what I want you to help your student learn to do is to look at this and find a pattern. Matter of fact, they'll probably be better at it than you are. Notice, if I play around with this for just a minute, if 3 watches and 3 calculators are $99, then it must be true that each pair of a watch and a calculator must be $33. Isn't that logical? Once you see it, it becomes extremely obvious. So if a watch and a calculator is $33, then I can take this fact and go back up here and say a watch and a calculator, that's $33. Well, if that's $33 and a watch and a calculator is $49, then I must be spending $16 on a watch. And there you have it. That's not an Algebra 2 problem. That's a 5th grade math problem. Certainly you could check it. To check it, you would have to then say, if a watch, go back to my picture analogy, my watch and my calculator are $33, and if the watch is 16, then I know the calculator must be, I didn't do this before I started, 4, 10, 17. And so if the watch and calculator are 16 and 17, then you could certainly add those together and find that those give you 49, and of course the other one gives you 99. It becomes so obvious you practically don't need to check it because it's just logic. Isn't that lovely? You see what I mean by nice problems? They really make them work out. If you find the pattern you're looking for, it works out really easily. And as it turns out, the next couple of problems are the same type. See if you can work out the same kind of problems. In this one, we have that 2 bags and 4 hats are $100. Now, I could try to draw a bag and try to draw a hat, but the truth is my drawing is not good enough to do any of those things well. And so 2 bags and 4 hats is $100, and I know that 3 bags and 7 hats is equal to $164. Now I hope you pause and give yourself a chance to find a way to solve this. Pause the recording, look at it yourself. But if you've paused and you've looked and you hadn't found it, I'll go ahead and show you what we have. Notice that I could divide this group Actually, I started the wrong group first. It's all right, I'll go back and show you. Meant to start with this group. This group can be divided into 2 groups. That didn't work. Try that again, sorry. That's why I sometimes pause and do the drawing first. Okay, so what I'm trying to show you here is that a bag and 2 hats and another bag and 2 hats gives you $100. So of course that tells us that a bag and 2 hats must be equal to $50. So I have that here. That is $150 in 3 bags and 6 hats. And then I have another hat, and they told me that's $164. Well, clearly the hat must be worth $14. And that is a question it asks me, what is the cost of 1 hat? So you have to be able to look at the numbers and find some way to pair it up evenly. And when you realize that a bag and 2 hats happens twice in the first equation and it adds up to 100, then you can come up with this fact. And because it's a nice problem, you're just working with a 5th grader, we're not working on Algebra 2 today, because it's a nice problem, the second equation works in a similar way. All right, I paused so I could write it all down and not have you wait on me doing that. Number 8 tells you we have 3 watches and 5 lamps for $176. And then we have 5 watches and 3 lamps for $208. Now, these are nice problems, but we do learn new tricks for each one. I like to say in math, we're just working on our bag of tricks. We're expanding our bag of tricks with each problem. So in this problem, I can't really divide anything up nicely. Nothing works out like it did in the last problem. And so we need a new trick. We need a new skill that'll help us to do this. And so what we find is this lovely fact. If I look at these two together and I put all of my watches and all of my lamps into one big shopping cart, so to speak, then I have 8 watches and I have 8 lamps, and altogether I have $384. Now, let's divide that out into groups. Remember, if I have 8 watches and 8 lamps, I can divide them out into 8 groups, where each group has 1 watch and 1 lamp. And since 384 divides by 8 to give me 48, I know that each of these pairs of 1 watch and 1 lamp is $48. Again, you may be tempted to make an algebra problem out of this, but don't. You're working with your 5th grader. They're learning logic. They're learning math concepts. Let them learn it this way. Let them see what they're doing. It'll make all the sense in the world, and it'll make really good algebra students out of them. Okay? So, the question is, what is the cost of 1 lamp? And what we now know is that a watch and a lamp in this case I have 3 of them. I have 3 pairs of watches and lamps. So each of those pairs is $48. And then I have 2 lamps left over, and altogether that's $176. I'm going to write that down here so I can work on it. Now, you may be tempted to think this is an algebra problem. I promise you it isn't. It's just logic. Okay? Again, don't let you get all messed up by anything. All right? We're just saying that all of these together add up to 144. And the 2 lamps then must be equal to 32, because I need 32 more in this spot to give me 176. So if 2 lamps is $32, 1 lamp must be $16. And that is a question they're asking us for number 8. Problem number 9, we are told that 3 calculators cost as much as 7 mugs. So I've drawn a picture, and again, It's a sketch just like you and your kids are going to draw. Nothing's professional and perfect about it. But I've drawn a picture that shows 3 calculators that are the same length, the same price as 7 mugs. And then it tells us that each calculator costs $12 more than each mug. So how do I show that on my graph? Well, what I can say is then this is like a mug plus 12. Each of my calculators is the same as 1 mug, but it's $12 more. I'm trying to find the cost of a mug, and look what happens. If these are the same, then I can cancel out, I can subtract, I can get rid of 1 mug for each one. Remember, my drawings are the same, and I have 4 mugs left over, and I have $36 left over in my top picture. Remember, the 2 are equal. If a calculator is the same thing as a mug plus $12, then the picture shows that I have 4 mugs to be equal to $36. Remember, once you've drawn your picture and we have mug plus 12, mug plus 12, mug plus 12 like that, you can redraw it. I've redrawn on the right side of the paper. The same exact drawing is on the left side of the paper. On the top, we have mug plus 12 3 times. On the right side, I just reorganized them. I put all the mugs in front and all the 12s in back. And so what we're saying here essentially is the first 3 mugs and the first 3 mugs are the same, which tells me that these 36 and these 4 must also be the same. So if 4 mugs is the same thing as $36, then 1 mug must be $9. And in fact, that's what the question asks. How much is each mug? $9. Now, habitually, we're going to go back and check. If you have 7 mugs at $9 a piece, then that's $63 worth of mugs. If a calculator is equal to a mug plus 12, then that means each calculator is $21. And 3 calculators, 3 times 21 is also $63. So the price of 3 calculators and 7 mugs is the same, and that makes us all happy because we know for sure that we've answered our problem correctly. Number 10 is almost exactly the same problem. 3 jackets cost the same as 5 shirts. We know that each jacket is $16 more than 1 shirt. So if I take each of these jackets and I divide it up, I have the same thing as a shirt and $16 more for each one of them. Each jacket is the same thing as 1 shirt and $16 more. Now, if it helps you or your student at all to redraw that so you have them in a better order, certainly do that. It might be you have to do that a few times, and then after that you're good to go. But the jacket picture is the same thing as 3 shirts and then 3 16s. Now remember, the shirts themselves are equal to 5 groups, but these first ones are the same. Oops, that's supposed to match right there. Okay, 5 shirts is the same thing as 3 jackets, and a jacket is the same thing as a shirt plus 16. So then, clearly the first part, the 3 shirts and the 3 shirts are the same, and that tells me that the last part is the same as well, and I know that 2 shirts is equal to $48. So 1 shirt is $24. And that's what it asks. What is the cost of a shirt? $24. So again, check it out. 24 times 5. Each shirt is $24. Multiply it times 5 and you're going to get $120. If each jacket is a shirt plus 16, then a jacket is $40. And if I have 3 jackets, it is also $120. That means I checked it and it works out, and it makes me very happy to know I have the right answer. And that's the end of the challenging word problems for the whole number section.